Next, theorem 195. Now this one links the cycle space and the cut space of any graph. It states that they are orthogonal complements of each other. Now I am saying orthogonal complements, although this is not actually an orthogonal complement of a subspace, but something that is like an orthogonal complement. You remember, this thing arises from our definition of a function that looks like an inner product, although it really is not, between two sets of edges in any graph. Not going back to the actual definition of this, you already know what that is. But based on this function, we defined this orthogonal complement type of thing. Say we have a subspace F of the H space of a graph G. Then the orthogonal complement of F is defined to be the set of those elements, that is those H sets in the H space that are orthogonal to every element in this subspace. In this sense, this is equal to 0 for all F belonging to this subspace. So we have to now prove that these two are in such a relation to each other. And if you are wondering what this diagram is about, we are coming to it later. I have just simply kept it there. It has nothing to do with this. So let us now see the proof. Let G equal to V, E be any graph since the number of edges common between or common to a cycle and a cut in G is an even number, we have the cycle space contained in the orthogonal complement of the cut space. Now let us try to understand why this is so. So what we have written is that the number of edges common to any cycle and any cut in G is an even number. First we have to understand why that is true, and then as a consequence we have this. Then we have to understand that how this follows from this claim. Okay, so let us consider any cut in G. That means E of V1, V2. With that, to that thing we are going back. So for a cut, there will be a partition of the vertex set of the graph, that is V, into two disjoint subsets which are non-empty, whose union is V. That's what partition means. And the set of those edges, all the edges that run between V1 and V2, that is those which have one end in V1 and another end in V2, form a set of edges which we are denoting by this symbol, and such sets we have called cuts, right? And they together with the empty set give us a subspace of the edge space of G, that is our C star, that is the cut space. And on the other hand, all the cycles in G generate or span a subspace of the edge space, that is our cycle space. Okay. So now what we are saying is that if there is a cycle in our graph, now this in fact is our entire graph. We have all the, taking into account all the vertices in V1 and those in V2, we have all the vertices in G. And whatever edges the graph G has are present here. Some of them run between V1 and V2, and some of them stay confined here, some of them stay confined here. Now, in G, if we find a cycle, what we are saying is that the number of edges that will be there in the cycle as well as in this cut is an even number. That we need to understand now. Now, it may very well happen that the cycle we have considered has all its vertices lying in V1 itself. Then the cycle would look like this. But then the edges in the cut have nothing to do with the edges in the cycle. That is, the number of edges common to the cycle and the cut is 0. In this case, that common number is 0, but 0 is even. And the other case is that no, that's not the case. That is, some of the vertices in the cycle will lie on this side. Obviously, if the cycle is entirely on this side, that case is exactly similar to this one, so there is no point in looking at that. So the cycle has at least one vertex in V1 and also at least one vertex in V2. Now, if we start going from one vertex to the next in the cycle, following the edges in the cycle, that is, if we traverse the cycle, and say we start our journey here at this vertex, then no matter what the situation is, at one point or another, we will have to reach this vertex, since this is a vertex in the cycle, and that would require us to make a jump like this. We don't really know whether that jump will start at this vertex itself or at some other vertex of the cycle that lies in V1. But we will have to cross from this side to that side at one point or another. Also, after crossing, after going from V1 to V2, we may not land at this vertex itself, but maybe somewhere else. But keep in mind that since the cycle comes back to this vertex, so we will again have to jump from this side to this side at one point or another. And this may not happen just once. It may happen several times in general. Maybe the cycle goes like this, and then we come back to this. But then again, after some point, we may again have to go back to that place from V1 to V2. But because we have to eventually come back to this, so again we will have to make another such jump. That means in order to come back to the starting point, for every time you cross from V1 to V2, you have to come back from V2 to V1. And this creates an even number of edges, an even number of jumps, because if this number is odd, then you will stay in V2 itself. So then you cannot come back to this. But that's not what happens in a cycle. In a cycle, once we start our journey at one point, no matter how large the cycle is, eventually we come back to that. And that's why this number is even. But this number is what? These edges are some of the edges in the actual cut. These edges may not be all the edges in the cut, but they definitely belong to the cut itself, that is this set. And that's why the number of edges that are there in both the cycle as well as the cut is even. That's what we have written. But when we defined this inner product kind of structure, there at that time we also understood that this is 0 if and only if the number of edges common to F1 and F2 is even. So that means now if we were considering any cycle, right, the number of edges between the cycle and any cut we have found is even. So from that, how is it following that the cycle space is contained in this? Let us see. Say you consider a cycle. Actually, considering a cycle really means in the context of the things we are doing, the edge set of the cycle. Let F be the set of edges of a cycle in G. That just simply means that F is a vector in the cycle space, right? So according to this thing, and according to this criterion for such an inner product to have 0 value, this will be equal to 0 for any cut keep in mind that the cuts in C star are the vectors in C star. Besides the empty set, empty edge set. But the cycles in C are really not all the vectors in C, but rather they span C. But if this kind of inner products have 0 value, then definitely if in place of F you consider a linear combination of cycles, then that corresponding inner product will also have 0 value, following the properties of inner product, that this function, although it is not an inner product, also follows. So that is why you see that this F must belong to the orthogonal complement of C star. So f belongs to this. But f is what? F is an arbitrary cycle, or rather the edge setup in an arbitrary cycle. So f is an arbitrary vector from the spanning set of the cycle space, and all of them now belong to this subspace, orthogonal complement of C star, which is a subspace of the H space of the graph. So that's it. So if all the vectors in a spanning set belong to a subspace, then the subspace they span will be contained in this subspace, and the subspace they span is C. Hence, C is contained in this. Okay, so that's how we have got one inclusion. Now we continue our proof. So here actually I should put a bar, because all those explanations, they are not part of the actual proof given in the text. Conversely, then the author writes, conversely, it follows from proposition 192 that for any set of edges not in, well, if I just simply write not in C, that will look a little odd. Let me write like this. That is, if f is a vector in the H set of H space of G. In other words, if f is a set of edges in G, but that is not a vector in the cycle space, there exists a vertex phi in the graph that is incident with an odd number of edges in F. Now, where is this thing coming from? If you go to this proposition 192, there you will see that we have some equivalent conditions for a set of edges to be in the cycle space, and one of those conditions is that if f is such a vector, such a set of edges, then the graph whose vertex set is V, the entire set of vertices of the graph, and whose edge set is F, in this graph, which is a subgraph of the original graph, all the vertices have even degree. So now if we are considering an F which is not in C, then at least one vertex in this graph for that F should be there which does not have even degree. Now, not having even degree in graph is equivalent to being incident with an odd number of edges in F, naturally. But then what is the consequence of this? This implies that this inner product is not 0, that is, it is 1. Our inner product can have exactly two values, it is either 0 or 1. We already know that this kind of inner product has 0 value if and only if the number of edges common to f and this is even. But now what kind of vertex is this? Our vertex is say the vertex V is here. Now V is incident with an odd number of edges in F. So edges that are edges at V, this number of edges is odd. But these are edges which are elements in the set F. And what is EV? Do you remember EV? EV is the set of those edges that are edges at V. That is, you can say they are edges emanating from V. So this is a set of edges, that means this is a vector in the edge space, because this is just all the edges that are there in, well, this may not be all the edges that are edges at V, there may be others, but this is the set of those edges in E of V which are also edges in F, and that number is odd. So that's why this inner product value cannot be 0, it is 1. But then, since EV is a vector in the cut space of the graph, so this F is not orthogonal to all the elements of C star. We thus have F not belonging to the orthogonal complement of C star. In other words, that if we have taken F to be not in C, then it is not in C star perpendicular or C star orthogonal. The contrapositive of this statement is that if F belongs to this, then F has to also belong to this. That is, if then F belongs to the cycle space. So the orthogonal complement of the cut space is also contained in the cycle space, and the other inclusion we have already seen before. So combining these two things, you have equality. Hence okay, now we prove the other one. We have proved that C is C star orthogonal. Now we have to prove that C star is also C orthogonal. To prove it's enough to show that if we take the orthogonal complement of the cut space, then we get the cut space back. It follows directly from the definition of this. This is how the author wants to express it, but actually really it follows from the definition of orthogonal complement, that is the orthogonal complement of a subspace of the H space. That's what he means when he writes this. It follows directly from the definition of this, that this. But how? Let's see. So say we take an arbitrary vector here. Say we take f in the cut space of G. Then then what will be so what I am trying to so what do we have to conclude? That's what matters. No, I'm also getting confused. These parts are a little confusing. We have to be extra careful. We want to show that this f belongs to this space. That is, we want to show that f belongs to this. What does this mean? It means that we have to show that this inner product is 0 for all t belonging to C star perpendicular. This statement, just this one, not this one, okay, this one is logically equivalent to this. But now let us look at this statement. If you take any d from C star perpendicular or C star orthogonal, you want to prove that this inner product value is 0. But that is true, no? Because f belongs to C star. Now if d belongs to C star orthogonal, then by the definition of this subspace, this inner product will be 0. So that means this is the true statement, and that's why this is a true statement. And that is why, without needing anything else, just from the definition of orthogonal complement, it follows that we have this. Now we go for the reverse inclusion, but this is where that dimension formula comes into play, which is that if you add the dimension of a subspace of the H space and its orthogonal complement, then you get the dimension of the H space itself, which is m, the number of edges in the graph. Now we know that the dimension of our original subspace is the cut space plus the dimension of its orthogonal complement is the dimension of the H space of G. But just like C star is a subspace of the H space, C star orthogonal is also a subspace of the H space. So a similar dimension formula applies to it as well. Plus this, and which you can clearly see if you cancel this from both sides, you get these two dimensions to be equal, which implies that the dimension of the cut space is equal to the dimension of the orthogonal complement of the orthogonal complement of the cut space. So C star is a subspace of this and they have the same dimension, so they must be identical from vector space theory. Thus, we must have this. Okay, so that proves our claim, and it also completes the proof of this this theorem. Right, so now we come to now let us see what comes next, and this is where we have this figure. Now let G equal to C comma E be a connected graph, say, and let, I need ink, what, have I run out of ink? Just give me a moment, okay? For some reason it's stuck. Yeah, now it came out in a spark. And in this connected graph, we are going to consider a spanning tree. We already know from our study about trees that such a thing always exists in any connected graph, and not just a spanning tree, but a normal spanning tree with any vertex as root. If you go back to those results, you will see that. Let this be a spanning tree in G. For any edge E not belonging to the tree itself, that is, which is an edge in the original graph, but it's not an edge in the tree. For any such edge, there exists a unique cycle CE in T plus E. To see how you go back to that tree result, the main result in the section on trees and forests, there you will understand what this C is. In other words, if you join any two non-adjacent vertices of a tree, you will get a graph that is T plus E, in which there will be precisely one cycle having that edge as one of its edges. And this kind of cycles have a name. They are called fundamental cycles. These cycles CE are called the fundamental cycles of G with respect to the spanning tree T. On the other hand, if you choose an edge now from the tree itself, if E belongs to the edge set of the tree, then so this is the result I was talking about from Theorem 151 part 3. The graph T minus E has exactly two components. That is, you are removing one edge from a tree. That will give you exactly two components. The set of edges DE between these two components forms a bond in G. Or D, I need to write between these two components. So you can see that thing here, right? So what you are looking at is a graph in which you are looking at a spanning tree, or maybe the author has drawn a part of a spanning tree. Anyway, so you have the spanning tree here or a part of it. The dashed edges are not edges in the tree, and you have this single edge E which is there in the tree. So you can clearly see that in the part that you can see here, if you ignore the dashed edges, then you get a tree. In that tree, say you remove this edge, then the tree gets divided into two connected components. That means the resulting graph has two components. To show where those two components lie, we have this line partitioning it into two parts. One part lies on this side, the other part lies on this side. Now, what we are saying here is that all the edges between these two parts, between these two components in T minus E, form a bond in G. Do you recall what bonds are? Bonds are cuts that are minimal, and we have already saw how to recognize bonds. A cut will be a bond if and only if the induced subgraphs, that those two partition sets, having cuts means having those two partition sets and then seeing what edges lie between them, right? So the induced subgraphs, the subgraphs induced by those two partition sets, if they both of them are connected, then the resulting cut is minimal, it has to be minimal, and it's a bond, and conversely also it's true. So here you can of course see that if you just simply remove the edge E, you then have two bonds, but then you get sub trees which are connected. So that's why all these edges, all these dashed edges along with E itself give us a bond, and these bonds also have a name. They are called fundamental cuts of the graph. These bonds DE are called the fundamental cuts of the graph. With respect to of the graph G with respect to that spanning tree T. Okay. Now, why are we suddenly defining these things, fundamental cycles and fundamental cuts? It turns out that among all the cycles, the fundamental cycles actually span the cycle space. Similarly, the fundamental cuts actually span the cut space. And from that, one can guess the dimensions of these spaces. And this can be shown directly. However, there is a theorem that comes after that one that we have seen today that gives us more information about this whole thing. And let me now state that theorem. The proof we will not do today. We will start the proof from the next graph theory update. So the theorem is this. Let G be a connected graph and T a spanning tree. Then the corresponding fundamental cuts span the cut space C star of G and the fundamental cycles span the cycle space C of G, and if G has n vertices and m edges, then the dimension of the cycle space of G is m minus n plus 1, and the dimension of the cut space of G is n minus 1. Okay, so in the next graph theory update we will prove this and see some other things. This section is almost over. After seeing these things, we will eventually get to the notions of adjacency matrix and I think incidence matrix that can be associated with a given graph, and then we will see how those matrices are related, and this is where the section will end. And after this we have another section which is the last section of this chapter, where we will generalize the notion of graph itself to hypergraphs, multigraphs and all those things where multiple edges are allowed. So we will see these things. So I end the video here itself, and last Saturday I think we solved Gallian's group theory problems. No? So tomorrow let us solve Gallian's ring theory problems. So with that, see you tomorrow. Until then, this is me, Lucifer, from a mathematical group. Have a nice night.